Yeah, good evening, class. Welcome back to THE 451 Chemical Process Technology. We're starting with Module 5.1. Remember, we've done up to Module 4.3. So we're looking at Module 5.1 Mixing Processes and Mechanisms. That's the first part. We're going to look at mixing sensitive processes. We'll also look at mixing mechanisms of homogeneous systems, mixing mechanisms of heterogeneous systems, dimensionless numbers. We'll also look at dimensionless analysis for agitation fluids. And then we'll look at a group of dimensionless numbers. Don't mind, you have dimensionless numbers here, dimensionless numbers here. Here specifically, we'll look at the use of these dimensionless numbers in this fluid flow. And then here we'll look at other types of dimensionless numbers. Sensitive processes. Considering that a mixer consumes a determined amount of mechanical power. So a mixer consumes a determined amount of mechanical power depending on its shape, dimension, and agitation speed. These are the things that determine the amount of power a mixer consumes. It can be dissipated inside a vessel by reducing large flow rates, that is bulk motion, or high levels of turbulence due to liquid shear, that is shear stresses. Typically, axial impellers promote bulk motion while radial ones promote shear stress. So basically there are two types here now. We'll see to that: bulk motion and shear stress. So processes promoted by mixing may be classified on the basis of their sensitivity to 1. Bulk motion, 2. Shear stress promotion. Now for bulk motion control processes, those which do not need to create new interface, this includes blending, heat transfer promotion, or which must allow the availability of actual interface for exchange of processes, that's the solid suspensions. And again, shear rate controlled processes are those which efficiency rely on the generation of interface exchange surface, that is gas, liquid, or liquid dispersions. Now what we're saying is, for instance, if you're blending, you have some kind of homogeneous phase, which is what you want to achieve. Now, but in shear means you have, just like when we talked about momentum flow. In terms of momentum flow, we're talking about, shear rates, forces, where one liquid layer will be on top of another liquid layer will be on top of it, another liquid layer. So each of the liquid layers will be flowing at different speed. So when you are doing agitation, each of those liquid layers flowing at different speed. Imagine where, okay, for example, let's take something like some of these drugs taken by, children, some of the syrup. When you keep them, you find out that when it settles, you have two layers. Now, when you shake, you are trying to mix both the upper layer and the lower layer. And at the time you finish shaking, you see that what you have resulting will be a homogeneous phase. So there will be either the bulk moving, that is bulk motion, or one level will be moving against the other level. And that automatically is what will now agitation to be achieved. Mixing mechanism. Now the mechanism for these mixing processes follow different methods. One is molecular diffusion, and this occurs at the molecular scale or level. The second one is turbulent diffusion. Now we're talking about molecular diffusion is similar to when we talk about laminar flow or laminar diffusion. Now, turbulent flow, and this is caused by vortex dissipation. Vortex comes. An easy way to explain vortex: when you bring a bucket of water and probably you feel that water is dirty. Our normal non-conventional way or local way of filtering that water is you put your hand inside it. When you put your hand inside the bucket of water, you rotate your hand. The moment you rotate your hand, you find out that the water will start, moving in circular paths, and that the middle of the water will appear as if it is depressed. That is what we call vortex. The more you speed your hand, the more that middle goes in, and there's a way you increase the speed of your hand, and that part of your water will, pour away from that bucket. We'll still come to vortex to see the uses of vortex and why we'll not allow vortex to get to certain level. 3, convective diffusion. This is caused by convection occurring in large scale spaces. Now, convective flow breaks the liquid into large drops, that is macro mixing. The drops are then broken into smaller ones by vortex deformation. That brings about interdrop mixing. Now, those vortex breakage and deformation will increase or renew the contacting between drops with different concentration and promote molecular diffusion. Then we have a fully homogeneous mixing depends on molecular diffusion. So for us to get a fully homogeneous, these are the major 3 mixing mechanisms. And once we arrive at what we want, it means we have arrived at a fully homogeneous mixture. Now, in comparison, the turbulent diffusion is about 10 to the power 5 or 10 to the power 7 times of molecular diffusion and dominates turbulent agitation. So we have mentioned turbulence. We have also mentioned laminar flow. So we're saying that turbulence or turbulent diffusion is far greater than molecular diffusion. Another way to know turbulence or molecular, if you have a big tank that is filled with water, if you open that tank very small, you see water flowing, gradually in streamlines. But when you open that tap to the end, you see the water rushing out. That rushing out is what results in turbulent diffusion. The initial one is laminar flow or molecular diffusion. Okay, now we're at mixing mechanism of homogeneous systems. Now, 2 important things here is the viscosity of the liquid. So we have 2 of them: low viscosity liquid and high viscosity liquid. So for low viscosity liquids, large vortex is broken into smaller ones by shearing forces or shearing effect. The viscous resistance converts part of the mixing energy into heat. Strong mixing effect occurs at the zone near the agitator. Total circulation flow rate is most important for this type of mixing. So we have liquids that are, viscosity is small or low. Now, for high viscosity liquids, in the laminar zone, mixing depends on total flow. The agitator efficiency is low at turbulent zone. Large diameter, often close clearance, and low speed agitators should be used. Impeller must sweep the whole vessel volume to ensure good mixing. You see the conditions. Now, it's just like when you go to the market, some of these common blenders we buy these days, they will give you different impellers or different agitators and tell you that this one is used for tomato, this one is used for vegetables, this one is used for that. Now, these are the kind of things we're saying. If you use the wrong one for a solid that is stronger, and you use the one that you're meant to use for a solid that is not that strong, then you're likely to break or spoil that particular blender, that is the agitator. Now this is for heterogeneous systems. Now for heterogeneous systems, we have immiscible liquid-liquid systems. Remember, heterogeneous means it's not one phase. Homogeneous means they are all in one phase. Now for immiscible liquid system, one phase is continuous and the other phase is dispersed. You see, that's why we don't have one phase. For zone near the agitator, the shearing effect is strong under high turbulence and small liquid droplets will be achieved. In the zone far away from the agitator, the droplets will agglomerate into larger ones. Now this is what we are trying to break down what happens in the agitator. The breakage and agglomeration process increase and renew the interface of the liquids to strengthen the interface mass transfer. Remember, there's a mass transfer between all phases. We're talking about in terms of mass transfer. In fact, for agitation, there are different reasons. It can be to achieve homogeneous system. It can be to increase mass transfer. It can be to increase heat transfer, and so on, like we said when we started with mixing and agitation. So if a surface activation agent is added in the system, the agglomeration will be weakened and the size of the liquid droplet tends to be uniform. Mixing mechanisms of heterogeneous system. This is gas-liquid systems. Now for gas-liquid systems, the mechanism is similar to liquid-liquid systems, but gas is dispersed in the liquid. So gas-liquid interface tension is stronger than that of liquid-liquid, and the dispersion of gas is more difficult. Large density difference between gas and liquid makes the gas bubbles rise to the top of the liquid. High shearing agitators are often used to generate relatively small gas bubbles. Radial types are preferable to the other types of agitators. We also have solid liquid system. Now to suspend the particles homogeneously in the liquid, to reduce the thickness of the liquid film on particle surface in order to accelerate the reaction or transport processes. Like we said, it might be for chemical reaction, it might be for transport processes. Now, there's what we call critical speed of suspension. And this is the minimum rotating speed needed to suspend all particles. This is very important. It depends on the agitator size and as well the physical properties of that suspension in question. So this is the minimum speed, the minimum rotating speed that is required to suspend all particles. So if you go below that speed, you cannot suspend all the particles, and of course mixing cannot take place. Now the question is, why dimensionless numbers? Dimensionless numbers are used as empirical correlations to estimate the power requirement or power required to rotate a given impeller at a given speed with respect to other variables in the system. Now those variables are measurements of tank and impeller, distance of impeller from tank floor, liquid depth, dimensions of baffles, viscosity, density, and speed. All these things we will mention in detail when we talk about the design, or when we look at a common continuous stirred tank reactor. We'll see the tank size matters, the distance of the impeller from the tank floor matters. If it goes down to the floor, it means that when the impeller will be turning, it will be scratching the bottom of the tank, and that will cause a problem. You also have a liquid depth, so that if vortex forms, remember what I said vortex is. If vortex forms, if you fill the liquid up to the level of the tank, that means the moment there is vortex, part of the liquid will pour away, and you would have lost part of your raw materials or even products. Then there are baffles. Baffles are constructed by the sides of the tank. Now baffles could mean that same water bucket I mentioned initially. As you're turning it, if you put your hand by the sides of the bucket, you will see that your hand will disturb the rotating of that water. That's the way baffles work. By putting your hand there, you will now make the entire liquid to mix again. So baffles help in achieving greater mixing. Of course, viscosity, density, and speed of the liquid is very important. Now, these are dimensionless numbers. We have met Reynolds number before. This is called power number, pumping or flow number, Froude number, and Weber number. All these dimensionless numbers are used in fluid flow in one way or the other. But the important thing is that when you now check the units of all these things, you find out that each of them will give you a dimensionless quantity. Each of these units will cancel out. We did that with Reynolds number. So take your time, put in the units for all these and then see whether it can cancel out. The conclusion of this module 5.1, we've looked at mixing sensitive properties, we've looked at mixing mechanisms, we looked at mixing mechanism for homogeneous and heterogeneous systems. We have also looked at dimensionless numbers. Thank you very much for listening. I expect to see you in the next class. Thank you.